Okay, welcome to Ramsey. And on behalf of the Colloquium Committee, I'm Tom Junk, and one of the reasons why we're here today is because of the scheduling of this result with the publication ended up on a Wednesday, so now it's a colloquium instead of a wine and cheese. And because the quantum people took one west, here we are in Ramsey Auditorium, which is a really nice place. So many thanks, Yanki, for providing this, and it's great. So without further ado, let's introduce our very own Matt Toops, the co-spokesperson of MicroBooNE, along with Justin. Matt? I don't see Matt. Yes, Justin, you please be Matt.
I will be Matt. Matt's up there. Are you coming down, Matt? Can I hold fort for a minute while we bring you down here? Certainly, on behalf of myself and Matt, we're very pleased to see you all here today. Thank you for coming to see the release of this result. Matt, I'll hand over to you.
It's great to be here. Should I do another lap? Thank you so much for coming. We are so excited to share with you this result published this morning on Nature. Before we get started, I'd like to invite the lab director, Young-Ki Kim, to say a few words of welcome and maybe something about neutrinos and the importance of this result for the lab. Young-Ki?
Well, I don't want to talk about neutrinos because speakers will talk about neutrinos, but this is super exciting. I'd like to thank Justin and Matt to lead this collaboration and coming to this outstanding results. I have to look at it. I have to listen to our judge whether. But this anomalies has been going on for what many days, decades. So I'm super excited that we have some conclusive conclusive conclusion sounds funny, and this is again very impactful to our science and especially particle physics. So I very much look forward to listening and congratulations to MicroBooNE collaboration. And this is our 10th anniversary, so it's a perfect time. So well done.
Thank you very much, Young-Ki. One quick note, we will have a reception following the colloquium, so we'll have the colloquium, then a Q&A, and then a reception afterwards, so please stick around for that. And so on behalf of Justin and myself, I'd like to invite our first speaker, Hanyu Wei, professor at LSU, up to start our presentation. Thank you.
All right. Good afternoon, everybody. I'm Hanyu Wei. I'm an assistant professor at Louisiana State University. This is my colleague, Sergey Martynenko from Behavior National Lab. We'll give today's talk together. Why doesn't it work? Okay, good. As advertised this morning on social media and various venues, and MicroBooNE has reported a landmark sterile neutrino search and using the first ever 2-beam and 1 detector setup. This result was published in Nature earlier today. And it's a pleasure and honor for Sergey and me to present this result on behalf of the whole MicroBooNE collaboration. Okay, neutrinos. So why study neutrinos? Neutrinos remain some of the most intriguing particles in the universe and constantly challenging what we think we know and pushing physics forward. So they open a unique window for probing some big questions, and such as is the standard model of elementary particles complete possible extensions, and why is there much more matter than antimatter in the universe, and how does a supernova unleash its energy that seeds the next generation star, and how does black hole emerge from collapse of massive core. And all beyond that, could there be entire sector of the universe, dark particles, and dark forces that we've never seen and shape the cosmic evolution from behind the scenes. And neutrinos sit right in the middle of these mysteries. They interact rarely. Therefore, they are able to carry critical information from extreme environments in nature and provides one of the cleanest pathways to new physics beyond the standard model. So that's why we study them and use them as the most powerful tool for discovering what comes next. In the standard model of elementary particles, neutrinos are fermions, the matter particles, come in three flavors: electron neutrino, muon neutrino, and tau neutrino. And second most abundant in the universe. They have no charge, no mass, and interact. They are only weak forces. And one of the features that makes neutrino especially fascinating is the oscillate, transformed from one flavor to another as they travel. This implies they are not massless and inconsistent with what the standard model tells us. And this is a simple two-flavor neutrino oscillation probability, sinusoidal, as a function of L over E, and L is the neutrino travel distance or detector baseline relative to the neutrino source, and E is the neutrino energy. In the two-flavor picture, let's assume only electron neutrino and muon neutrino. The flavor eigenstates are superpositions of the two mass eigenstates, and the mixing can be described by this 2x2 rotation matrix with one parameter theta, a so-called mixing angle. And each mass eigenstates will pick up different phase value, m squared times L over E, and the phase difference will be proportional to delta m squared times delta m over E. That drives the oscillation probability shown here. And this factor is the sine squared 2 theta. That is the mixing angle. Back to this plot. Assume only muon neutrino produced at the source. And the blue curve is the nu mu disappearance probability, and the red curve is the appearance probability of the other flavor. If a detector sits at the right baseline and red energy, and it can observe either an excess, one flavor showing up unexpectedly, or a deficit of the flavor produced at the neutrino source. Okay, this oscillation pattern can let us extract the mixing angles, and the amplitude give us the mixing angle, and the frequency let us extract the underlying mass squared difference, which is the delta m squared term here. For example, the super K experiments, the spectrum from atmospheric neutrino oscillation, so the 1/2 deficit let us extract the corresponding sine squared 2 theta value. In the NOVA experiments, the spectrum from accelerator neutrinos, and there's a dip here, and the position of the dip correspond oscillation maximum, help to review the underlying mass squared difference. The Juno result, the first Juno result released 2 weeks ago, there's also a dip, different position, and review a different mass squared difference. Okay, in the full three-flavor picture, the flavor states and mass eigenstates mixed and can be described by a 3x3 unitary matrix, and we call it PMNS matrix. And each pair of mass eigenstates contribute to a two-flavor mixing-like parts, something like that. The super K NOVA contribute to this part. And other experiments using reactor neutrinos and solar neutrinos and map out the other two parts extremely well. Put them together, three mixing angles, 1, 3, 1, 2, and 2, 3, and two distinct mass square difference corresponds to these two characteristic L over E scales of 10 to 3 or 10 to 5 kilometer per GeV or meter per MeV. All right, over the past decades, extensive experimental results align beautifully with the standard three-flavor framework, observing oscillations at the two characteristic L over E scales we just discussed. However, a few experiments have reported anomalies due to possible oscillations at much, much smaller L over E. This reminds us of solar neutrino anomaly 60 years ago, and where detectors observe a 30 to 50% deficit in solar neutrino flux led to discovery of neutrino oscillations. So what would these anomalies tell us? And let me briefly review them first. LSND and MicroBooNE, new appearance anomalies. Electron neutrino showing up unexpectedly. And in this talk, the new E may refer to both electron neutrino new E or electron antineutrino new E bar. But in this slide, I'll distinguish them. The LSND experiment was to measure nu E bar from a mu plus decay at rest source. And the muons come from the decays of the secondary mesons and generated by a proton beam striking target. But in this neutrino source, the flux, neutrino flux, is nu E or nu mu bar dominated. Electron neutrino, red, and the muon antineutrino, the cyan color. And this monoenergetic corresponds to muon neutrino from pion decay. So as we see here, negligible electron antineutrino component. So however, in the LCD experiment, this measurement, so it observed a significant excess of electron antineutrino. And this excess, where do they come from? So it can be interpreted as a nu mu bar to nu E bar oscillation, where the nu mu bar comes from this. And this excess covers the L/E range from 0.4 to 1.4 meter per MeV, much smaller than the two characteristic L/E scales we just discussed in three-flavor scenario. Okay, mini-bone appearance anomaly. So mini-bone experiment motivated by the LSND anomaly was to measure electron neutrinos from a different neutrino source, decay in flat source. So the neutrinos come from meson decays in flight rather at rest. So this neutrino have much higher energy, so GeV or sub-GeV scale. So this is the flux of the mini-bone experiment, which is also a flux used by MicroBooNE. We'll discuss later. So the y-axis is log scale. So the red curve represents the nu E component, which is very, very small, just a sub-percent level. And the mini-bone observed a significant excess in this measurement. So the data represented by the dots, error bars, and the stacked histogram represents the prediction of the expected number of events. And this excess covers a LV range, and similar to the LSND anomaly, and also can be interpreted as the oscillation from nu mu from the source to nu E. If we put together the nu E bar access to prediction ratios from different energy beams, from different baselines of these experiments, and expressing them as an appearance probability, we get this plot as a function of L/E. And the black curve represents the underlying appearance, nu mu to nu E appearance oscillation probability, right? Something like this. And this angle, mixing angle, sine squared 2 theta mu E, is dedicated to nu mu to nu E appearance channel. All right, so if we map these parameters onto a 2D plane of sine squared theta and delta m square, that is what they look like. And we call extended areas allowed regions. And they are extended because they reflect the uncertainties in the measurement. And the allowed regions of LSND and a mini-bone cluster together and at EV scale delta m square. In addition to nu E appearance anomalies, and there are nu E disappearance anomalies, and from gallium experiments or certain reactor experiments. The gallium experiments, GALX, SAGE, BEST, so they use radiochemical detectors based on gallium that can only measure total interaction rate. So they measure electron neutrinos from some radioactive sources, corresponds to a few discrete sub-MeV energies. And they constantly observe a 20% deficit and of the electron neutrinos produced from radioactive sources. And this deficit can be interpreted as a disappearance effect of the nu E produced at the source. And L/E values correspond to a few discrete points ranging roughly from 0.5 to 2.5 meter per MeV. And the neutrino 4 experiment measuring electron antineutrinos from a reactor core observe a oscillation pattern in a similar L/E region. So this is a lot of regions from neutrino 4 gallium anomaly. The x-axis is sine squared 2 theta EE, so we use theta EE for nu E to nu E disappearance. If we put back the appearance channel, and we notice that they point to a similar delta m square scale, the EV scale. This is 0.1, this is 10. So the oscillation hypothesis and provides a plausible, testable, and very natural explanation for all of them. Okay, back to this slide. So several anomalies due to possible oscillations at a small L over E, and corresponds to a very high Dardan square, inconsistent with these two known mass splittings, and imply existence of an extra heavier flavor and mass eigenstates, and commonly called a sterile neutrino, so which has no standard model interactions. And in this talk, we'll focus on such EV scale light sterile neutrinos producing a small L over E oscillation. And in the 3+1 framework, this is additional flavor, nu S sterile neutrino, and this is additional mass eigenstates M4. And the Dardan square we discussed in previous slides is actually delta M square 4(1). And ignoring the difference amount M1 to 3, and they are very, very small compared to M4. And if such a sterile neutrino can be found, it will be a beyond standard model particle and reshape our understanding of mass generation, lepton number variation, such kind of things, and profoundly impact particle physics, extraparticle physics, as well as cosmology. Okay, MicroBooNE, focus of today's talk, has already contributed to the sterile neutrino interpretation of these anomalies by searching for sterile neutrino-induced oscillations. This is our 2023 result, an old result, and we set a constraint in this 2D parameter space. And this constraint corresponds to a exclusion curve, and meaning the oscillation parameters to the right side of this curve corresponds to stronger oscillation signal would have stood out clearly in our data. But because we saw no oscillation in our data, this region was excluded. It's the exclusion curve. And in addition to this MicroBooNE old result, earlier experiments, mostly accelerator experiments at the short baselines or low L over E, and set their respective constraints in this 2D plot, and because they saw no oscillation in their data. And as we see, this is the accumulative exclusion curve represented by solid black line. As we see, the 3+1 sterile neutrino model is still an open possibility. And there's another channel. Okay, new MicroBooNE result. So it'll be very exciting to see a new MicroBooNE result and see how much it can contribute to clarifying this picture. There's another channel. New E to new E disappearance channels, as you remember. And the constraints from the earlier reactor neutrino experiments, the prospect, stereo, and have ruled out most regions allowed by the neutrino 4 and the gallium. And with the most recent result from Katrine, and the Katrine released its latest sterile neutrino search result earlier today in the same issue of Nature, together with the new MicroBooNE result, but use a different method. It's not oscillation-based method. It's based on the beta decay spectrum kink. All right, but Katrine is more sensitive to high Dardan square region above the scale in this plot. But with this, the new Katrine result, I think, if I'm not mistaken, the entire regions are excluded. So this channel is very interesting, a very interesting situation. But it will be also interesting to see whether new MicroBooNE result can see something on it using a very different neutrino source. Okay, where is MicroBooNE and what is MicroBooNE? So MicroBooNE sits on the booster neutrino beam line of Fermilab, the booster neutrino beam, and uses 8 GeV proton beam bombarding target somewhere here, producing neutrinos and passing through our detector. And the MicroBooNE detector is 70 meters upstream of the mini-BOONE detector here along the same beam line. So it can provide the direct test of the mini-BOONE anomaly. But MicroBooNE uses a very different detector technology, liquid argon TPC, a combination of liquid argon calorimeter, high resolution, facing time projection chamber. So liquid argon TPC enables a powerful neutrino flavor reconstruction and selection. And MicroBooNE's L over E ranges from 0.2 to 2, so it can probe the EV scale sterile neutrino oscillations, for all the anomalies we just discussed. Okay, the strategy of the last sterile neutrino search at MicroBooNE. 3+1, so one additional sterile flavor, and full 3+1 analysis, meaning all detectable oscillation effects are considered in our data, including new E appearance, new E disappearance. This is what we just discussed, and also new to new disappearance, and nu E to nu mu oscillation, nu E nu mu to nu tau, or nu stereo. But these two channels are negligible in our data, and they correspond to a very small number of electron neutrino events or neutral current events. So the three main oscillation effects are considered here. We perform a simultaneous feed on all available nu E and nu mu interaction channel in our data. And this way, we can also reduce the shared systematic uncertainties and improving the sensitivity. So this is actually a multi-parameter problem, but we can project our result onto different 2D planes and directly compared to the available a lot of regions reported by these other experiments. So in addition to the nu mu to nu E channel, as we just mentioned, we also set constraints in the nu E to nu E channel, though this sensitivity is not very competitive. Okay, so the sensitivity of the old result, 2023, is much worse than expected, and mainly due to a degeneracy in oscillation parameters. And this is the challenge that we need to deal with, and what it is. The basic idea is the appearance and the disappearance effect in nu E spectrum can cancel each other. So the oscillated spectrum is indistinguishable from non-oscillated spectrum. For example, this is non-oscillated spectrum, nu E, and this is the energy spectrum. If you only consider disappearance effect, a small fraction of nu E also is missing, so times PEE, like nu E probability. If we only consider appearance effect, a small fraction of mu neutrino oscillating to nu E and added on top of beam nu E events. So if the appearance effect happens to offset the disappearance effect, that is what we have. The net oscillated spectrum is the same as the non-oscillated. That is the region of the degeneracy. But we have nu mu spectrum, if you remember. We fit to all nu E and nu mu. But here, the nu mu spectrum provides little help with this situation. The reason is, even if the appearance effect is as large as the total nu E events from the beam, this P mu E, nu mu nu E oscillation probability is still a very, very small number, as there is only a tiny nu E component in the saturated neutrino beam used with MicroBooNE. And also, in general, a saturated neutrino beam, nu E component is very small. So that will result in a basically invisible disappearance effect in the nu mu spectrum. All right, so degeneracy arises. These two effects cancel each other, meaning the ratio of these two mixing angles equal to the beam nu E to nu mu ratio, which is almost a fixed value for different energies in the beam, meaning there's also no shape information that we can use to disentangle the appearance. All right, fortunately, MicroBooNE has two beams. So this is where the MicroBooNE's unique capability comes in. So in addition to the booster neutrino beam on axis, and we see neutrinos from a different beam, the neutrinos and the main injector, 8 degrees of axis MicroBooNE, use a very different proton beam in striking the target. These two beams have very different nu E component. So this is the flux from the BMB. Only about 0.5% nu E, BMB beam, and for nu me, about 4%. So if we calculate the beam nu mu to nu E ratio, BMB 200, nu me 25. So 1 order of magnitude smaller. So meaning they have quite different degeneracy points if we use single BMB or single nu me beam to do the oscillation search. So we have two handles to lift the appearance and the disappearance degeneracy. How? What happens if we combining these two beams? We made this plot to demonstrate this. So this is a coordinate frame. X and Y axis are the ratios of oscillated and to non-oscillated nu E events in BMB and nu me. So these two dashed lines mark the degeneracy point. This is for BMB, this is for nu me, correspond to different ratios. This is the nu E to nu me ratio from the beam. So where do those mixing angles sit in this plot? Here we go. So we add some curves, and each curve represents a constant value of the oscillation parameter. For example, the red one corresponds to sin squared 2 theta EE dedicated to nu E disappearance effect. And this greenish curve represents a constant value for another angle, sin squared 2 theta mu e, nu mu to nu e appearance effect. And the nu mu to nu mu disappearance effect makes the angle can be determined if we know these two values, and they are correlated. Okay, so if you take a look at this intersection where we have sin squared 2 theta e 0.1, sin squared 2 theta mu e 0.002, that is what we have. This set of parameters will produce a stronger appearance effect in nu e spectrum, resulting in net excess in BMB nu e spectrum. The same set of parameters will produce a stronger disappearance effect, resulting in a net deficit in the nu e spectrum. But we don't need to do this calculation. We can directly read this information out from the coordinate frames. So here, the BMB sits at 1.1, meaning 10% excess, and BMB 0.96 is a 4% deficit. So if we place the full 2 degrees encoding the values of the mixing angles, and x and y axis tell us the nu me and the BMB excess or deficit with the corresponding oscillation effects, and we can relatively straightforward to sense how the degeneracy is broken. For example, we can scan along this line, corresponds to BMB degeneracy point, because the ratio is always 1 for these oscillation parameter values. The BMB no change, and the nu me deficit, if you take a look at the y-axis value, rapidly grows with an increasing sin squared 2 theta e, meaning we can disentangle the disappearance effect from appearance effect. And also, based on this plot, we can sense BMB is more sensitive to appearance effect because the gradient of these curves is roughly along x-axis. And the gradient of the sin squared 2 theta EE disappearance effect is roughly along y-axis. So nu me is more sensitive to disappearance effect. Sergey will discuss further about that. Okay, we can use more accurate predicted nu e spectrum to cross-check this understanding. So nu e spectrum BMB, nu e spectrum nu me, this is where we start. So no oscillation effect. So we scan different sin squared 2 theta EE, sin squared 2 theta mu e change accordingly. And that is what we have. So BMB nu e spectrum barely shift, but nu me developed a pronounced deficit with an increasing sin squared 2 theta. Meaning we could use nu me to constrain disappearance effect. Subtracting disappearance effect in BMB, then we can probe appearance effect. So that is what we do. All right. So the new result, released in today's Nature, use the first 3 years of BMB and nu me data and combining these two beams together, unlocks the full power to test the 3+1 model and compare to a lot of regions by the reported anomalies. So the dotted blue curve represent the new sensitivity of today's new result. And we achieved 0.1% sensitivity in this new appearance channel, capable of testing these anomalies. And in the nu e to nu e disappearance channel, we also achieve a competitive sensitivity compared to Catrain and Prospect. And but we use a very different neutrino source, so much higher energy, GeV sub GeV compared to MEeV or sub MEeV usually used in this. All right, I'll stop here and hand it over to Sergey, who will walk you through the analysis and the results.
Fantastic. Right, thanks, Hanyu. Right, let's talk about MicroBooNE 3+1 result. But before talking about the result, we need to discuss several pieces that actually, in combination, gives us better understanding of the result we have. So we need to discuss our data, our event selection, systematics, and statistical analysis. Starting with our data. As Hanyu already mentioned, we do have 2 beams, and across 2 beams, we use half of available MicroBooNE data for this analysis. With BMB beam, we reached about 6.4 10 to 20 POTs, and for nu me, we reached about 1 10 to 21 POTs. The most important part about these 2 beams for our result is that BMB, it's almost pure nu muse, and it's very sensitive to nu e appearance. And nu me has a much larger nu e content and more sensitive to nu e disappearance. Right. That's our data. For event selection, our event selection starts with our detector. And for detector, we use a low energy threshold fully active liquid argon calorimeter and the high energy and position resolution time projection chamber. This detector is excellent at identifying different species of particles and reconstructing 3D images with fine-grained precision. Here on the right, you can see the event display from our detector. You can see a vertex of neutrino vertex very well. You can see a couple protons coming out, shower from pi naught decay, maybe delta ray and pion here. But one of the important qualities of the detector is our electron-photon separation power, which we do in 2 steps. First is dQdx, which is ionization energy loss, is 2 times different between 1 electron and a photon. And also, we are looking for a gap between the vertex, neutrino vertex, and the start of the shower. This enables our high-performance NUE selection out of overwhelming nu charge and neutral current events. All right, the reconstruction in our detector is performed using wire cell package in 4 stages. It starts with noise filtering and signal processing. Then it comes to 3D imaging, clustering, and charge light matching. Then we do 3D trajectory and dQdx fitting and cosmic muon tagging. And lastly, we do multi-track fitting, 3D vertexing, and particle identification. For neutrino energy, we use calorimetric reconstruction, which means we sum the reconstructed kinetic energies of all the particles in the event. We add rest mass values for muons, electrons, and pions. And we also add average binding energies per nucleon for each proton we see in the event. With this, we achieve a good resolution of about 15% and bias of about 10% for our neutrino energy reconstruction for our NUEs and NUMUs. And this performance is similar for both BNB and NUME beams. Right. With this selection, we can take a look at our target channels, which are obviously NUEs. And they are not, don't see the data points just yet. We will put them on later. But what you can see here is the green colors, which is our NUE and anti-NUE CC selection for BNB on the left and NUME on the right. You can also see these blue patches here. It's our NUMU and anti-NUMU CC selection. And the other shades of green, it's our CC pi naught and NC pi naught selection. So the main takeaway here is that we have very pure selection of NUEs, and the main backgrounds are NUMUs and pi naughts. Right. But it's not just these channels that we use. We have a lot more. So let's walk through all of them. First of all, we split our NUE CC channel into fully contained and partially contained. The reason is based on reconstructed particles are fully in fiducial volume or not, and that gives us increased statistics channel. We also do have sidebands. That's our NUMUs, also split in fully and partially contained. And our NUMU channels are meant to constrain our NUE prediction due to universality of cross-section modeling for CC interaction and common hadronic parentages. And also we have 3 pi naught channels, CC pi naught fully contained, partially contained, and NC pi naught. And pi naughts are a major background for our NUE search because it mimics NUE signature. All of these channels, which you can see 7 of them here, but in total there are 14 because there are 2 beams, are fit simultaneously in our analysis. Right. Let's go through these sideband channels one by one, starting from our NUMUs. So here on the left, I always show BNB. On the right is NUME version of our NUMU selection with good high squares for both of them. But also you can see that both of them have MC under prediction, which is still consistent at 1 sigma level. I'll get back to the NUME part of this slide later in the talk. But for now, let's move to our CC pi 0 selection, again with BNB and NUME having a good data Monte Carlo agreement. And last but not least, our sideband, it's NC pi naughts, and again BNB on the left and NUME on the right have a good data Monte Carlo agreement. All right, that concludes our event selection. So let's talk about our systematics. We have three main sources of systematics. It's detector systematics, cross-section, and flux. Let's start with detector, right? So we have a range of tools that we use to characterize our detector. It's cosmic muons, protons, laser. Like example, you can see here on the right. We can plot the reconstructed entry and exit position of cosmic muons. But then we evaluate a range of systematic effects, like covering light yield, space charge, combination, wire waveform simulation. Like on the right, again, you can see the effect of space charge. So in perfect world, the positions should lie nicely on the angle here, but they are not because of space charge. So we compare our data to Monte Carlo to assess the magnitude from each of the effects, and we use modify Monte Carlo samples to assess the impact of these uncertainties on the analysis. All right. The second one is the cross-section. But before the uncertainty, a couple words about our cross-section model. So for cross-section model, we have a base cross-section model, which is GNV3, and it's shown as a blue line here on the plot. But when we do tune it to T2K, nu mu CC 0 pi cross-section, which are data points here on the right, and that's how we obtain our base MicroBooNE tune model, which is the red line here. Then we can use this model and vary a set of cross-section parameters around it, like line here, and the various set of parameters, which is like total of 57 of them. We obtain this 1 sigma band. And we can propagate the same parameter variation to the event rates to build the covariance matrices. And here, the example of like actually correlation matrix, because it's easier to read. How you can read this, B&B correlations are bottom left and nu mi on top right, and they split in nu e's and nu mu's. And the one, which is yellow, is basically the highest correlation, right? So you can see immediately that nu e's and nu mu's are highly correlated for both beams. And that's, as I mentioned, because of universality of cross-section modeling for CC interactions. We can leverage these correlations to constrain the cross-section model and its uncertainties. So as an example, let's take a look at our uncertainty band for B&B nu e selection, and here only cross-section systematics. And we can constrain our B&B nu e's with our B&B nu mu's. Right? And you can immediately see that due to high correlation, the uncertainties significantly shrunk. All right. The last but not least, systematics is a flux. And before talking about flux systematic itself, a couple words about our flux model that we updated prior to this analysis. Why we started looking at updating it. So at 8 degrees of axis, for nu mi, flux is quite different from the traditional on axis. Here on the left, you can see B&B flux for nu mu's, and on the right is nu mi flux for nu mu. For B&B, most of nu mu's comes from pi nodes. But for nu mi, there is a higher fraction of kaons plays a role. So model must account for kaon production very carefully. But then we started looking at available models. We understood that they disagree significantly. For example, here there are some available models which are Jant for 10, 11, and for 10, for 11, and for 9, shown in different colors. And there is not much data that exists to constrain the K+ production in nu mi beam. So what we did, we used the base model that agrees best with available data for us, which is Jant for 10. And we applied the very conservative uncertainty up to 40%, where there is no coverage based on the model spread. All right. This slide basically shows the summary of what went into our updated flux. We did update some beamline geometry. We updated our baseline model. We introduced constraint from NA49 and others similar to NOVA and Minerva. And we did very conservative treatment of uncertainties outside the data coverage. On the right, you can see the ratio of old to new flux for nu mu's on the left and nu e's on the right. With new flux, we can again take a look at our correlation matrix for two beams, for nu E's and nu Mu's. And same thing here, BNB is at bottom left, and nu Mi is at top right. You immediately can see that between two beams, the correlation is part here is basically 0, because we treat them as uncorrelated, because they have a different hadronic processes and beam energies. And also for nu Mi beam, correlations are much stronger because they have a higher fraction of K pluses, as we discussed, and it's also a dominant decay for nu E's. So that's why the correlations are very high. And also for off-axis beam, there is a high number of re-interactions, which also contributes to this high. So as I promised, we are kind of getting back to our nu Mu sidebands, and there is a way how we can validate our nu Mi flux modeling using our BNB data. So as we discussed, BNB and nu Mi correlated in detector and cross-section systematics, but their flux systematics is uncorrelated. So what we can do, we can constrain our nu Mi nu Mu selection with BNB nu Mu's, right? What it's going to give us, the detector and cross-section systematics would largely cancel out, leaving us mostly with flux. And also, the nu Mi prediction will be updated based on BNB data. So let's take a look at this constrained nu Mi nu Mu spectrum, which is here in blue. So you immediately can see that there is a good data Monte Carlo agreement. The updated prediction agrees well with data, and uncertainty here is dominated by the flux. So with that procedure, we consider our nu Mi flux model validated. All right. So we kind of discussed these three pieces. All of them come into our statistical analysis. And to understand the result, we need to remind ourselves of this equation, which is the probability of oscillation at short baseline for different neutrino flavors. But most important part for us here, it's the sine square 2 theta alpha beta, which obviously can be different based on what you are trying to calculate. For nu appearance, it's sine square 2 theta mu E. For nu disappearance, it's sine square 2 theta EE. And for nu Mu disappearance, it's sine square 2 theta mu Mu. In our analysis, we explore actually right part of these equations. So we explore 3D parameter space in delta M square for 1, sine square theta 1 4, and sine square theta 2 4. But all the results are given in 2D, in delta M square for 1, sine square 2 theta mu E, or EE, right? So to do so, we do profiling over sine square theta 2 4, which basically minimizing high square over the one axis and calculating then the result in 2 dimensions. Right. This is the full high square that we use. We discussed our measurements, we discussed our prediction, and covariance matrix that's come into it. It's also worth reminding that this high square that we use, it includes all 14 channels simultaneously. And how can we use it? Here is the pipeline that we follow in our analysis. First, we can get best fit value for oscillation parameters in 4 new hypotheses. When, with best fit, we can do a data consistency test against 3 new hypotheses using Feldman-Cousins procedure. And after, we can set limits via frequency CLS method if the data consistency passed. OK. So now, all these pieces come together into our results. And we can start with putting data points on our target channels, starting from the BNB. So I'll show nu ECC channel here on the left, and its nu Mu counterpart for this beam on the right. This one is not new. We published it in 2023, but still, it's worth reminding us that we do have a small deficit here in BNB nu ECC channel, and we do have access in Mu. But the interesting thing that happens in our 14-channel simultaneous fit is that our nu Mu's will be constraining our nu E channel, updating the prediction and potentially pulling it up based on new data. OK. This one is new. So that's our new selection. On the left, again, it's new ECC channel. On the right, it's our new muse. And both of them has a small data Monte Carlo offset. But as in the same sense as BNB, in our simultaneous fit, new muse will constrain our new ease, updating prediction and reducing the normalization offset, as you see here. Let's actually illustrate how this constraining procedure works. Let's isolate these two channels, BNB new ease and new me new ease here. And without constraint, high square is about 37.9 for 50 degrees of freedom. But then we can constrain it with all non-new channels that we got. And we have this blue line here. And with constraint, high square increase a little bit to 41, which makes sense because the uncertainty is shrunk. But this pull of the prediction up is coming from new muse, as we discussed, because most constraining power comes from new muse. And that's how our constraining procedure works in our new channel. The other interesting thing to look at here is how our fractional uncertainties change in our new ECC selection, because after all, we are statistics limited analysis with dominant systematics being flux and cross-section. And what we really need is to reduce our uncertainties for better results. So here is fractional uncertainty without constraint for BNB and new me new ease. Then we shrink the systematic uncertainties, and we get this black line, which is already significantly reduced fractional uncertainty. But also, as you remember, the prediction for both BNB and new me is pulled up, which is further reduced the systematic uncertainty, and higher for new me's because the pull up is higher for new me's. Okay, so with this data, we finally can go and follow our statistical analysis pipeline throughout. So starting with best fit values. Here it is. So our best fit values here on the left, and we compare this best fit line, which is for new best fit, red line here, with non-oscillation prediction, which is in stacked histogram for BNB on the left and new me on the right. Basically, you can see almost no difference between them. The reason is because we got this very low delta M square for one, which leads to negligible oscillation effect. If this best fit, we can get test against three new hypotheses. To do so, we use Feldman-Cousins procedure. So we throw about 10,000 toys, and we get this nice distribution of delta high square. And we can put our data, delta high square, which is around 0.2, very close to 0 here. And that gives us p-value of about 0.96. What this p-value means? It means that BNB and new me data is consistent with three new hypotheses. Right. Now we can go ahead and set the limits, since we know that the data is consistent, three new. And we can start discussing our limits with our students channel. So first, there is our sensitivity. So we compare our sensitivity, which is this blue line here, with our previous BNB only result, which is our red line here. So sensitivity obviously improves with respect to BNB only case because of degeneracy. We mitigated the degeneracy of oscillation parameters and also new me, new e contribution in this channel. But now, where actually our data stands? So let's take a look at our data exclusion. So that's our data exclusion. This is solid red line here. And you can see that MicroBooNE at 95% confidence level in this channel excludes most of gallium allowed region and parts of neutrino 4 allowed region. We also can put our data result in the perspective of our Brazil band around our median sensitivity. So here, blue line is median sensitivity. Green band is 1 sigma, and orange band is 2 sigma bands around it. So you can see that data exclusion is mostly weaker than the sensitivity and lays primarily inside the 1 sigma band. Why is that? So we need to remember that disappearance channel is more influenced by the nu-me because it has 4 times more nu-es than BNB. And nu-me, after constraint, data matches prediction very well. But still, BNB data has this deficit that weakens the nu-e disappearance limit. Okay. Now we can go through same logic with our appearance channel. First, comparing our sensitivity with our previous result. And again, our sensitivity improves with respect to BNB only case because of degeneracy mitigation. But now we can finally take a look at our exclusion limit at appearance channel. And that's how it looks. This solid line with huge jump in high delta M square. And we exclude at 95% confidence level, LSND 99% allowed region. And also we exclude vast majority of mini-BooNE 95% allowed region. Right. Same logic with disappearance. We can put it in context of our Brazil band around median sensitivity. You can see again that our exclusion limit is stronger than median sensitivity, and it lies in the border of 2 sigma region. Why this is happening? Let's take a look. Again, we get back to this constrained nu-e predictions for BNB and nu-me. And what we need to know about this appearance channel is that it's dominated by the BNB beam because it has 4 times less nu-es and 2 times more nu-mes than nu-me. And this BNB, it has a data deficit that boosts nu-e appearance limit, which basically favors smaller appearance angles. But also there is another way to look at this result, right? For this, we need to step back and remember our BNB only result. So here it is. These red lines show BNB only full 3+1 result that considers appearance, nu-e disappearance, and nu-e disappearance all together, with solid line being data result and dashed line being sensitivity. And obviously, the result is the data result is slightly stronger than sensitivity because of the BNB deficit. But what we also published back in 2023 is appearance only result, which is unphysical in our case because it disregards any effects from nu-e disappearance and nu-e disappearance, and this black solid line here. And it's obviously stronger than our full result because it doesn't have any degeneracy coming from these channels. But what it also shows us, basically the limit that can be reached with BNB only data if there would be no degeneracy of oscillation parameters coming from other oscillation channels. So let's overlay this appearance only result with our new 2-beam full result. So you can see that they are almost similar except this small part around 2e square. And the reason for this is that basically nu-me provides a maximum degeneracy mitigation to BNB dominant appearance channel. And that's why we reach this limit. All right. So just to summarize what I've discussed right now. So we saw no evidence for 3+1 sterile neutrino model. We exclude at 95% confidence level the 3+1 explanation for LSND and mini-BooNE anomalies, and exclude most regions allowed by the gallium and neutrino 4. So, and with that, we close the window for 3+1 model as an explanation for long-standing LSND and mini-BooNE anomalies. And here, I'll get the torch back to Hanyu to put these results into a broader perspective. Here you go.
Okay, thank you, Sergey. Presentation. Good to see you again. So now I'm going to wrap up today's talk and with an outlook where this takes us next. So as Sergey just summarized, the 3+1 framework no longer provides a variable explanation for the LSND and the mini-BooNE anomalies, but those anomalies, the observed excess data, haven't gone away. So do the reactor and gallium anomalies, and they also remain unexplained. And these anomalies continue to drive a global program of current next generation experiments aimed at resolving the remaining possibilities. I just list some of them, not exhaustive. And many of these experiments can provide a direct test of these anomalies as they employ similar neutrino sources, similar detector configurations, or in a similar L/E range. And many of them incorporate more advanced detection techniques or detector technology, so more sensitive investigation of these anomalies. And among these experimental efforts, a central program is the short baseline neutrino program at Fermilab, so which is an extension of MicroBooNE with 2 additional liquid argon TBC detectors at different baselines. So the near detector SBND and the far detector ICROS. So the near far detector configuration can substantially reduce systematic uncertainty in flux, cross-section, and detector, and improve sensitivity. And also the SBND detector in close proximity to the beam target and ICROS, very massive, and both fully operational and have already collected the largest statistics of data in the relevant L/E region. So this enabled SBN program to provide a high statistics, low systematic exploration of the less sterile neutrino oscillation. And not only new E appearance or new E disappearance, as we just discussed, but also the new mu disappearance channel, and to which the MicroBooNE alone has very limited sensitivity. All right, in addition to sterile neutrino oscillation search, the SBN program can provide a more comprehensive and sensitive exploration of a broader landscape of beyond the standard model physics as well, some of which will be highlighted in the following slides and with relevance to the LSND and the minimal anomalies. All right, for example, expanded sterile neutrino models. This includes possibilities like 3+1 and plus additional sterile flavors, +2, for example, or 3+1 and augmented by new dynamics involving the sterile state. For example, non-standard interactions, decaying sterile neutrinos, and some other examples. So MicroBooNE has begun exploring the 3+2 framework and is actively investigating the 3+1 plus decay scenario. In addition to sterile neutrino oscillation searches, non-oscillation searches targeting photon final states are making significant progress towards alternative explanations for LSND and minimal anomalies. So because the electromagnetic signature in the excess events may arise from photon final states, which convert into a pair of electron, positron, rather a single electron from oscillated neutrons. And the excess photon final states may come from unexpected or underestimated standard model processes. For example, the delta-related decay, single photon, coherent single photon production from full current interactions. And MicroBooNE recent analysis saw no sign of excess in these 2 standard model processes, but we do see an interesting 2 sigma excess in a model agnostic inclusive single photon search, particularly in this 0 proton channel. As shown here, these 2 beams, 100 to 300 MeV, and this is a 2. So this motivates further investigations in MicroBooNE and SBN. All right, another active frontier is a broader landscape of dark sector models. And for example, the neutrino-induced upscattering, dark matter particle-induced upscattering, or heavy neutral decay, and generated from the beam target. And many of these models predict photon final state or direct the E plus, E minus final state. So signatures that MicroBooNE or SBN can identify with high precision, as we just discussed in the photon studies. This is the event display of a E plus, E minus signal and from a dark sector model simulation in MicroBooNE liquid argon TBC detector. And recently, MicroBooNE released the world's first direct search for dark sector E plus, E minus signal as the possible explanation to the minimal anomaly. This is the result. This is data with error bars. We saw no sign of excess of such signals compared to the green dashed histogram representing typical E plus E minus signal from dark sector model. All right, but alternative dark sector models, particularly those with very different characteristic angular distributions of E plus E minus pair or energy distributions, and remain compelling targets and for further investigation of MicroBooNE and SBM program. All right, I'll finish up here and back to the main results discussed today. So using the first two-beam, one detector search of its kind, MicroBooNE sees no sign of sterile neutrino-induced oscillations in the relevant L over E regime, and closing the 3+1 window associated with the anomalies. With this chapter settled, the path is now open for new ideas and discoveries in future theoretical and experimental efforts. More to come. Stay tuned. Thank you for listening.
Great. Thank you, Hanyu. Thank you, Sergey. Even though I've known about those results for quite a long time, though, it's still really nice to see them up there on the screen at last. So, and it's really nice now to actually get the opportunity to start hearing some feedback from all of you outside of the collaboration on these results and to get your questions. So I think we now have about 10 minutes to take questions. So please. See one up there. Three up this side. Go for it, Tom. Yes.
Me first. Okay. First of all, huge congratulations and thanks for beautiful results and also beautiful talks. I really like the results in your talks. I have a question. So you said that you have very negligible detector systematics, regardless of you have NUMI beam or not, right? Did you say that you have small detector systematics? Negligible systematics for detector.
Not negligible, but not dominant.
Yeah, not the dominant. Yeah, yes. Compared to the other two. So that's true for you even though you don't use any NUMI beam. So detector systematics is still small, no matter what you use NUMI beam or not.
Yes.
Okay. So how did you achieve such a good detector systematics?
A good detector.
I think that's good detector design, the whole collaboration, tremendous effort to calibrate detector, better understand detector response, also produce some detector variation samples, something like that, help us to estimate detector systematic uncertainty in the high precision.
Okay,
yeah.
So that's one thing we need to learn from you. And another one quick question is that, so the last slide of your Hanyu's talk, so you compare the sensitivity with 2023 and the current sensitivity. So I see that the bigger sine square zeta values. So your sensitivity degraded with NUMI beam. So why is that? So higher
you mean at the bottom here?
Zeta.
You mean bottom or
yeah, bottom.
Here?
Yeah, those higher sine square 2 zeta UE. So you see the current sensitivity is degraded compared to the 2023.
Well, because it's not exactly apple-to-apple comparison, right? Because here we compare data result with the sensitivity result. So
2023 is the data
yes,
result.
So it would be more fair to compare sensitivity to sensitivity.
I thought those
then there would be converging at this point, and that's going to be fine.
It would be good to see some apple-to-apple as well.
But this is data, so it's kind of a little bit to the left.
Okay, thank you.
In the future, on the SBM program where you have two detectors on the BMB beam, how useful will the NUMI beam be? Or will you need it at all?
Right. To me, I think at NUMI beam will further boost the sensitivity in SBM program. So ICRAS can see the neutrinos from NUMI for sure. And also, though we have near-far detector, but there's still sort of degeneracy. NuMe can help. But this degeneracy will be a bit, weaker as we have, near-far detector at different bases. But still, the NuMe can help.
There's another one up there, Tom.
All right. Thanks for the talk. This is great. It's great to use NuMe Beam to do the searches. I had two quick but highly correlated questions. One is, what is the NuMu bar contamination in NuMe off-axis?
Do you have this?
This is negligible. Let me find the flux somewhere.
I'm not sure we have a breakdown for NuMu, anti-NuMu, but it's a small fraction.
Yeah, percent level.
Oh, percent level?
Yeah.
Yeah.
Okay.
And in our selections, it's also very,
Yeah,
very
it's bigger than NuE, but much smaller than NuMu.
Wait, but NuE contamination is 5%. So then NuMu can't be percent level. It needs to be like, what, 20%? I think my question is if anti-NuMus are relevant for this, and if they are, how do you correlate the cross sections? Because the anti-NuMu cross section will have a very different Q-square dependence, and it will lead to very different topologies in your detector, right? So your NuMu sample may have a much larger contamination from NuMu bar, which will change the efficiencies I would expect due to topology.
We have the NuMe spectrum somewhere.
I don't have a breakdown for NuMu, anti-NuMu here.
But our cross-section model, treat NuMu and the NuMe bar differently. And that information will go into prediction, for example, in this predictive spectrum, as well as in the systematic uncertainty estimation.
Yeah, the key thing is that that will be in the covariance matrix. It
Right.
will be accounted for.
We just do not distinguish NuMu bar here in this plot.
Yeah,
Oh.
but in general, we do.
Yeah.
Yes.
Okay, thank you.
Tom, there's a couple of questions down here. I can't see them at the top, but there's one there, and then Young Ki has one over here. Yes, and then we'll, okay. That's a good question.
Can I ask something? It's not directly related to MicroBooNE.
Go ahead.
Or Catherine.
Catherine, yeah.
What's going on? Do they have any results with the mass, neutrino mass?
Neutrino mass.
Yeah, that was the main goal for this.
That was the main goal. Yeah, they
Yeah.
did release something at Neutrino, didn't they? Now, what is the new Catherine result? Oh, it's about. It was
So you mentioned about their.
Well, yes. Their paper that came out today was a sterile neutrino search.
I understand,
Yeah.
but I was curious
Yeah.
what's going on with their main goal.
Yeah.
Mango still mass.
.4.
0.45
0.45.
EV. That is the current limit.
0.45 EV.
My voice may or may not support this question. I was watching as it went by. You showed us more than a dozen fit results with chi-squared over number of degrees of freedom. They were all less than 1. Statistics doesn't do that. So somehow the errors are too big.
I know exactly where to go. I mean, yes, the errors are big. The errors are conservative, but what we are doing in the end, I'll show you constraint plot.
Constraint plot.
Far back. Yeah, here we go. Here we go. This one.
Yeah.
Yeah. So yeah, because after constraint, the uncertainty shrunk. So yeah, we do have a conservative uncertainty that in simultaneous 14-channel feed would be shrink due to the correlations that from our high statistics sidebands.
in many of these plots, all of these plots are correlated with each other. They're all showing much the same distribution in different ways. So I think in a feature of a somewhat systematically limited analysis, once one of your plots has a chi-square per degree of freedom below 1, given that a lot of these systematic error bars are highly correlated across their length, any distribution you make from that data is going to be sort of similarly correlated in a way.
Even the top left plot's a little, 9 out of 25, even by itself, all one is a little unlikely, but yeah, I'll give you one.
Oh yes, no, it's a systematically dominated analysis with a highly correlated bin-to-bin systematics.
Thank you very much for the nice talk. Could you go back to the slide with the neutrino energy estimate? I have two questions. So first of all, what is the source of the binding energy value? The 8-point-something MeV, I think. And the second thing, if you could produce better energy estimate for neutrinos by including neutrons, something like that, could you also get further improvement in the sensitivity?
For your second question, the answer is yes. And I think there is some works on deep learning energy estimation that for MicroBooNE that actually might go later in the analysis, can potentially boost the sensitivity. And for the second question, I missed it.
This
the binding energy.
Second question.
First question, I missed the first question.
Binding energy.
What's the source of the binding energy?
Yeah. Source of the binding. From a paper, some measurement, a test, some, yeah.
Mm-hmm. Okay. I see.
Yeah.
Because values keep changing, so I was curious about it.
Right.
Thank you very much.
But that one also did some study. We can vary that a little bit, so the impact is not very.
Oh, sure. Thank you.
Any more questions? Oh, there's one. Thanks, Pedro.
Okay, sorry for dominating that, but just one more question, I promise. Do you have sensitivity to NUMU disappearance? Because if you can do the appearance at 10 to the minus 3 and the NUI disappearance at the 10%, it feels like you should be able to get NUMU disappearance at the percent level, right? So did you check?
Yes, check that. It's not that sensitive, but we can provide some result constraints, but didn't publish that result in this nature.
But is that at the 10% level or the 1% level?
10% level.
So, okay.
Yeah. So that is basically the uncertainty in the new mu spectrum. But in the new E, that is something different because that sensitivity is basically shrinked because the new mu to new E ratio is very, very high. We measure the new E, but come from new mu.
Okay.
Right? But new mu disappearance is still in new mu channel. So that sensitivity will correspond to the uncertainty in.
Okay. New mu disappearance is very hard with a single detector. A dead record of your spectrum. You don't have this new mu to new E constraint. You can't use that in the same way to think your uncertainties. So that is somewhere where you really need a multi-detector SPM program to do a good job there. Right. I don't think I saw any hands, but if there is one, one more.
So if I'm following what you said earlier, then you have your systematics are correlated bin to bin, and you've not taken out a separate global systematic. If that's the case, then in fact, if you had accounted for that as a global, you would have had a much worse chi-squares. That in turn would have decreased your sensitivity in each of your points. And basically, it sounds to me, now that, in fact, what you've done is you have overcoverage, and your limits actually should be weaker. I'll leave that to you to think about.
Yeah, so, I mean, it's not clear why that would make the limits weaker at all, certainly to me. I mean, the frequentist CLS method that we do at the end, you know, takes into account all of the possible uncertainties in the covariance matrix as we do the fake data experiments, and that's how we calculate the exclusion region.
And also there's a strong normalization systematic uncertainty, something like that. But if you remember the preceding band of the sensitivities, and we add 1 sigma, 2 sigma band around the median sensitivity, we do see, you know, our data exclusion result is consistent with any reasonable result or uncertainty.
The uncertainties are correlated. You did it the same way. That's fine, but I'm questioning whether the methodology is right if you have a global correlated systematic, which needs to be accounted for only once.
But the constraint basically reduce the systematic.
Doesn't matter. There's still a global effect.
Yeah.
Right? If there's a global effect that's going to shift the whole thing up and down, then that should be counted once and not as part of a broader bin-to-bin.
So you can account for a global normalization shift in a covariance matrix. It just looks like a flat covariance matrix, but you can encode that type of uncertainty in a covariance matrix, and so the normalization uncertainties that are a part of this analysis are encoded in that covariance matrix. You get the same result as if you took it out. So it's included.
I think one more question down here, and then I think we have to wrap up. So we've got time for one more question, and then we actually have to leave and get to the
Should we go online?
reception. So yeah, it'd be one more. So if you want one more question, Sonny, go for it.
Okay, so I just want to make sure that I understood you correctly. So the reason why you have much better, sensitivity with the NUMI beam is not actually because of NUMI beam. That's because of you constrained with, even BNB beam, you constrained with the other, channel. I mean, disappearance channel to appearance channel, right? That gives a huge reduction. So this plot is a little bit, not this plot, so 2023 versus 25 results comparison could be a little bit misleading because the main reason could be due to NUMI beam, but it's not NUMI beam. Really. Even the BNB beam, you can reduce a lot with the, constraining. Is that correct? Did I understand it?
I would say mostly correct. I think that the power of this channel comes from BNB beam. But the question is, if we just do a single BNB beam study, if we do 2D comparison, so there will be degeneracy. The NUMI help to break the degeneracy, to unlock the power from BNB. As I mentioned, so here this sensitivity comes from the very large NUMI-NUMI ratio, but that is only true for BNB, not NUMI.
Mm-hmm. Okay, maybe I want to talk to you more later.
Great, thank you. Right, so the reception, I think, is outside 1 West. So yes, please do now all head up to the atrium, and thank you very much for coming.
Thank you.